Okay, students, this is a particular problem. I think it's number 21 in the section that had to do with position functions. So this is a recent problem in AP Calculus, and if we can read this together. Suppose a velocity function of a particle moving along particular axes is 20 squared 20t squared minus 110t plus 120 feet per second. And the particle starts at the origin at time is equal to 0. Use your graphing calculator to generate the graphs of, now watch it, s of t, that's the position function, v of t, the velocity function, and a of t, which is the acceleration function for this particular problem. So let's look at it. Okay, let's take a look at what we have here. So in this particular instance, remember this is it's just a line, and your dot is traveling to the left and the right on this line. Now they give you the velocity function. So if you notice, this is a quadratic, right? Okay, we're measured in feet per second. And of course, this is just given information. Now, what we're going to do is we're going to use a graphing calculator. But first, let's just use a little common sense. This is the velocity function. Remember, the distance, the derivative of the distance function is the velocity. The derivative of the velocity function is the acceleration. So what I did here is I took the derivative of velocity, and I've got this equation right here. And then I did an antiderivative, and I got this expression over here. Okay, now why do I have nothing over here? Because at time is equal to 0, the position function 0, so that c is 0. All right, now I just used my understanding to get my mind around the problem. And let's take a look at the velocity function first. Okay, so I plugged that in for y1, and I need to set my window. For my window, I'm going to go 0 to 5, and then I'm going to hit zoom fit. I forget now what number zoom fit is at. Oh, that would not be good. Go this way. I'm thinking it's 9. I'm not sure. Our zoom fit is, wow, that wasn't good. All right, sorry about that. So it's 0, okay? I'll remember that next time. So here I hit enter, and notice in the diagram, here's my velocity, okay? So can we explain a little bit here? Well, yes, we can. I'm having an object that's is traveling pretty quickly. It slows down, okay? It slows down, and it stops right here, okay? But then it turns around and goes backwards. It starts picking up speed. It slows down, and then the velocity is 0. So instead of going toward me, it starts going away from me, and it picks up speed. So that is what's happening. Now, what we want to do is we want to graph these other functions just to take a look at what's happening. What I'm going to do is I'm going to show you what to put in your calculator. All right, so I would put the velocity function in y sub 1. I just showed you how to do that, okay? So we just did that. Then in y sub 2, the problem said show the acceleration function. Okay, well, the derivative of the velocity is acceleration, so we're going to put that in y2. And the way you do that is you go to the math feature of your calculator, and you put this hold on a second. And you put this command in here, and you put y1, x, and x. Okay, so that's what you do there. Maybe I should just show that to you. Let's see if I could do that. Okay, so I'm over here, going to go down to y sub 2. And I'm going to go to math, numerical derivative, which I think it's down just a little bit here. Okay, so that's 8. I'm going to paste that here. I've not seen this before. So I think we're going to put x here. Then we're going to put y1 in here. Okay. Now I'm not exactly too sure what is going on out here. I think we should just put an X here. Okay. All right. Let's see what happens when we hit graph. Okay. So remember, this is the derivative of the velocity function, which is the acceleration function. Okay. We'll pause it. Okay. The next thing we're going to put in here is the integration of the velocity function, which should be the position function. This is the command, and this is the information we're going to put in for the argument of the calculator function. So here we go. Let's get the calculator out. And we're going to hit y equal. And we're going to go down a couple. All right. We're going to go to math. Let's see. It's probably 9. Okay. All right. Now, I'm a little confused here. Okay. So we're going to put 0 for the lower bound. We're going to put x for the upper bound. We're going to put in y1, so that's vars, y1. And our variable of integration is x. Okay, so let's graph this and see what happens. Now, this particular procedure in your graphing calculator does take a bit of time to do, and it's doing the integral of the velocity. Now, notice what's happening. This is supposed to be the position function here. So remember what I said, the object is moving away quickly, it slows down, it starts coming back to me, and then it slows down and goes away. So that is exactly what we would expect from the way I described that parabola in the first place. All right, but we're not done yet, okay? Let's do this. Let's actually, in y4, put the position function that we figured out earlier, and in y5, put the acceleration function in there. So let's see. Going over to the equation editor, we'll leave those there, and in y4, I'm trying to remember here, what was it? Okay, so it's 20 x cubed divided by 3, and that's minus 55t squared, or x squared, plus 120t. In this case, x, right? Okay, now what we're going to do to make this interesting is we're going to, boy, there's got to be an easier way to do this. We're going to go to the beginning of the y sub 4, and I'm going to hit enter, enter, enter. Okay, and I call this feature paintball with paint, and I call this feature paintball without paint. And we're going to leave that right there. Then in y sub 5, I'm going to put just, actually in y sub 5, I'm going to do that same thing too. I'm going to do paintball without paint. See what we got. Just got to keep hitting that. That's a lot of work. Okay, so here we go. We're going to put in here, well, we figured out 40x minus 110. All right, that is enough, folks. All right, let's hit graph. Okay, now what it did is already graphed the other functions. So now it's going to y4, and it's graphing what we figured out using the antiderivative. It's graphing the position function. And notice that this is exactly what we figured out using the capability of the calculator to draw the antiderivative. And when we get through with this particular part, we'll see what happens with y5, which is the acceleration function. Okay, and again, here's the acceleration function. So the little yellow paintball is really graphing y5. And you don't see it graphing it because we already have that line graphed previously by using the numerical derivative of the y sub 1, which was a velocity function. All right, so I hope that makes sense to you. Okay, students, what I did is I went into my calculator and I changed my mode to parametric mode, and I went under y equals, and I put our position function in here, and then under y1 I put 0. I changed my graphic to paintball without paint, and I set my window to these values. T min, T max, step, X min, X max, X scale, Y min -2, Y max 2, Y scale 1. And then what's going to happen is when I hit graph, it's going to graph what is happening with this, my little ball. So it goes to the right, then it's going back toward the origin that's negative. Remember, it speeds up and then it starts slowing down. And at a certain point in time, then it speeds up again, going to the right. So hopefully this makes sense. So that's question 21. I hope that helped you out. Maybe that gave you some more interest in the problem. Good luck with your class, and keep moving forward. Thanks.